Good afternoon. So I'm going to take the week 8 NPTEL live session here for the course which is entitled as Introductory Organic Chemistry II. And the course instructors are Professor Harinath Chakrapani and Professor Nirja Deshaputre. So in today's class we are going to discuss the different types of rearrangement reaction and as well as name reaction. So we'll solve the question based on these two topics. So let's move to the question number 1. Question number 1 is identify the major rearrangement product of the following reaction. So as it is mentioned in question, it is a rearrangement reaction, right? So rearrangement reaction is there, that means some bond is going to rearrange. So in your question you have given this structure and we have acidic condition on arrow, right? So what will happen in acidic condition? H plus will be generated, right? So if we will do H plus will be trapped by any of the these two carbon, right? But as all of you know that about the stability of the carbocation. What is the stability of carbocation? Yes, sorry. So this is the trend of carbocation stability. We can say the stability. So primary carbocation are the least stable, right? So here if we will see that in these two double bond, if protonation will happen here, then carbocation will be generated over here, this center, right? This center. But if the protonation will be done over here, then carbocation will generate at this center. So it's in between these two carbon, the carbocation will be stable on this carbon atom. So that's why carbocation will be generated over here and protonation will happen on this carbon. So here we have remaining structure as it is. Okay. Now here rearrangement will takes place. Rearrangement. So this carbon, if you will see the migratory aptitude, either the here one H is there, right? Either proton can be rearranged or this carbon or this tertiary substituted carbon. So according to the migratory aptitude, this tertiary substituted carbon will get rearranged. It will get migrated over this carbon and carbocation will be generated on this carbon center. So the migration will takes place like this way, and here carbocation will be generated. Why the migration is happening? Because of the stability. Because if you will see here 4-member cyclic ring is there, 4-member cyclic ring. But if it will become pi member, it will become more stable. So stability is the driving force, or we can see the reason for this type of migration. And again the carbocation is also stable. So after this one, Cl manase will trap this carbocation to give the alpha substituted CLI. Okay, this is the product you will get by this rearrangement. So here in this 4 option, which is the correct answer? Now you can compare the answer, and all of you know that according to our mechanism, this is the correct answer. Okay. Now let's move to the next question. Question number 2. Here the question is about what is a major product formed in the following rearrangement reaction. So here we have 3 steps. You can see first step is the Wittig reaction, then osmium tetraoxide reaction, then rearrangement reaction. So we will discuss one by one with mechanism. So here we have the Wittig reaction. So I think all of you are aware with this one. In Wittig reaction, PPH3, we can write this way also instead of writing this way, right? So if negative charge is there, right, so it will attack on carbonyl center. This negative charge will attack on this carbonyl center and it will form everything. Sorry, everything will remain as it is. Okay. Now this negative charge will attack on phosphorus atom and it will form four-member ring, phosphatin ring. Four-member phosphatin ring. All of you are understood till here? Now what will happen in next step? Elimination of triphenyl phosphine oxide will take place, followed by double bond at the place of carbonyl carbon. So this is the mechanism we are getting for Wittig reaction. So after getting this as a product, which is our first step, the further reaction will take place with oxonium tetraoxide. Oxonium tetraoxide. So have you heard about this reagent ever? Wittig reaction is so much popular, but have you ever heard about osmium tetraoxide reagent? What's the role of? Yes, hydroxylation on double bond. So what here we will get both OH group. So it is syn or anti OH groups. Have you heard about Woodward oxidation and Prevost oxidation? And what is the difference between Woodward, Prevost and osmium tetraoxide oxidation? Both are giving hydroxylation product only. All are giving the same product. Not same, OH group will be there. It could be anti, it could be syn. Yes. In Woodward, it's a cis hydroxylation, but at the hindered side. The mechanism is different. We will discuss in this class later. But in Woodward oxidation, we are getting the OH group on the same side, which is the hindered side. And the in Prevost oxidation reaction, we are getting both the hydroxy group on opposite side. We can say it's an anti-product. But in case of the osmium tetraoxide, it is a syn product, but the difference is that it approach through the least hindered side. Least hindered side. Okay. So I will show the mechanism here for osmium tetraoxide. So in osmium tetraoxide, I have shared later also, but here we will discuss in short. This is our osmium tetraoxide structure, and we have here this way. In first step, we have here olefin. Sorry for this one. I don't know what happening here. Here we will get this type of intermediate. This way, okay. We are interested in only this olefin reaction, so I am just drawing this part as it is. So here after this one, hydrolysis will take place, H2O, and it will give you a OH, OH, okay. So this is the way you are getting the product in this case. Now after getting this as a product, here the next step is rearrangement reaction. So which type of rearrangement reaction is this? Have you heard about pinacol-pinacolone rearrangement? Pinacol-pinacolone rearrangement reaction. So here the same thing will happen in third step after getting this step, this product. Where now pinacol-pinacolone rearrangement will take place, where in this case, sorry, this is not a type of pinacol-pinacolone rearrangement reaction. It is a type of this reaction, but it is in acidic condition. So here it will not happen. So here we have tosyl chloride, right? Tosyl chloride. So here this Cl manase will attack here. This will go out, knock out, and here we will get the. I'm writing directly from here. This. Okay. OH will remain as it is. Here we will get Cl. Cl. Now, this is a type of reaction rearrangement when here carbocation generation will take place when this Cl group will leave. So this is a leaving group. This is a leaving group here, and we will get here carbocation at this position. But as all of you know that primary carbocation is not stable. Always the secondary carbocation is stable. So that's why this group is migrate over here to generate carbocation at this carbon center. By this only, if you will see the migratory aptitude, you will observe that this migratory aptitude have some pattern where the carbon which is migrated first is given in a order. Here you can see, here we have OH group at second carbon, so that's why this carbon will get migrated and it will form a 7-member cyclic ring. Because earlier it was 6 members, so it will become 7-member cyclic ring, and you will see here carbocation generation will take place at this carbon center. Here this is the 7th carbon, and here we have, sorry, I have made here mistake. So listen here, carbocation migration will take place. So this will get migrated, not this one. So after migration we will get 7-member cyclic ring, and this is our this carbon, and this carbon is our OH. Here carbocation will generate at this center. If this group get migrated, here carbocation generation will take place. Sorry. Yeah. Now, after getting 7-member cyclic ring, carbocation is here, and now this carbocation will take a proton, which was earlier taken by pyridine. So proton, after taking proton, it will I have written wrong numbering. Okay, now I think it's looking fine. I have missed one carbon earlier. Okay, now it is fine. Yeah, so carbocation will generate over here, and this lone pair will push here to form a double bond. Now we will see here the double bond. So this is the answer we are getting by this mechanism. So this is the migration, again the rearrangement reaction. Here we are getting this as a 7-member cyclic ring as a product. So in this 4 option you can see that this is the only 7-member cyclic ring we are getting. So this is the correct answer for this question, and the mechanism I have discussed the way it will go. This is the way the mechanism will takes place. Now let's move to the next question. Question number 3. In the reaction shown below, identify the correct combination of intermediate P and the final product Q. So here you can see that this is again the rearrangement reaction. So we will discuss the mechanism, how it's taking place. So I have shown here mechanism. Here I am considering this as a R group. Okay. And in mechanism we will see that this is the Shapiro reaction. Shapiro reaction. So, so here till here we are given given in the question. Till here we got in the question. You can see that here we have this group already present, where we are getting from ketone here, right? Sorry. This is the product we have given. We have to start from here, and instead of tosyl group, here it is written SO2 aromatic ring, AR. Okay, so here when we will introduce the butyl lithium addition, here it is given already butyl lithium, excess of butyl lithium. Why excess of butyl lithium? Because here it is given 2 times butyl lithium, right? So excess of butyl lithium will be required for this type of reaction, and here butyl lithium will first of all, butyl lithium will give abstract the proton here. It will act as a base first. Okay, so when it will abstract the proton, negative charge will be generated over here, and it will be stabilized by lithium positive ion. And after getting this anion as an intermediate, in next step again butyl lithium will abstract the proton from another acidic carbon. So here it is the acidic proton. Acidic proton will be abstracted by butyl lithium. So that's why excess of butyl lithium is required. And after abstracting the proton, again the negative charge will be stabilized by lithium positive ion. Then this negative charge will push over here, and this double bond will push like this. It will form the intermediate of this diazo compound. Then, and this tosyl group will be knockout. After getting this diazo compound, again this negative charge will push electron here to form the stable N triple bond N, which is also a good leaving group, and this bond will come over here. So now, because N2 is the good leaving group, it will be eliminated, and it will give the intermediate, which is look like this one. Okay, this one. So in short, we can say that this whole group is going, and lithium is replacing this whole group, and double bond is shifting here, right? In short, so we can directly write here the mechanism in previous step, where yeah, our product should be like this one. According to our mechanism, right? We have discussed how we are getting this type of mechanism. Proton abstraction is taking place, right? First from this proton, then this proton, then carbon anion is generated. It will push here, it will go like this way. No, it will get knockout. Then negative charge will form another bond, and N3 elimination will takes place to give the product, this one. Okay, now check all the 4 options where this type of product you are getting. In case of the A, option A, it is incorrect. Option B could be correct option, and option D also. So these 2 are option incorrect. Now let's talk about the next step. So as all of you have seen that in previous step, we have shown that instead of when this lithium intermediate is generated, that time electrophile will be substituted instead of lithium ion. So this is nothing but equal to negative lithium positive. We can write this way also. So this negative ion could approach the electrophile to form the product. So we have discussed in previous case. Here we are getting the electrophile substitution, right? So here again the same thing will happen. We have here carbonyl carbon aldehyde, benzaldehyde. We have here benzaldehyde. It will approach over here, and it will give the product, which is like this, correct? So this is the product we will get by this rearrangement reaction, Shapiro reaction. This is the name reaction of Shapiro reaction. So here in these four options we can see that here the substitution is taking place at the position where lithium group is there, but here in fourth option it is not the same condition. So that's why this is the incorrect option. The correct answer for this question is option number 2. I hope you got the mechanism. Okay. Now let's move to the next question. Question number 4. Identify the major sorry, identify the major product of the given reaction. So now I have discussed in initial slide pinecolone rearrangement. So this is the example of pinecolone rearrangement where we are getting acidic condition. In acidic condition, this type of arrangement is taking place. Now we have two hydroxy group in this starting material, and here we have to protonate one of the hydroxy group. So according to the migratory aptitude, this carbon is going to easily migrate compared to the phenyl group. So and the carbocation stability will follow the will decide the mechanism. So as all of you know that we have two benzene ring over here, and if carbocation will generate over this center, it will be more stable compared to carbocation at this center. 1, 2. I am writing this way. If carbocation will generate at carbon number 1, it will be tertiary carbocation. It is stable but not compared to the second carbon. It is least stable, less stable, because in second carbon here two phenyl ring is there, aromatic rings are there, so this carbocation will become more stable compared to the first one. So that's why protonation will takes place on this hydroxy group. So I will write here this way. Mechanism, I am writing mechanism this way. So protonation is taking place at this carbon. Okay. Now after this protonation, this is the water molecule which will get knocked out to form the carbocation. Okay. Now because this carbocation is generated over here, so rearrangement will take place and this carbon will get migrated. After the migration, we will get 6-member cyclic ring instead of 5-member. This carbon is getting migrated over here, and here we will have both the phenyl groups, and here carbocation OH, right? Then it will push like this way. So because it is in acidic condition, it will become like this way. So this is the answer we are getting from this type of rearrangement. So this is the arrow pushing I have shown here, and the correct option in these four options is the second one. Okay. I hope all of you are understanding the mechanism I am discussing here. If you have any question, any doubt, you can interrupt in between and you can ask me. Otherwise, I will give a time for asking the question at the end of the class also. So today is last class. Okay. Now let's move to the question number 5. Yeah. Question number 5. What is the major rearrangement product of the following reaction? Sorry. So here I will discuss the mechanism. I have shown here already. So in this case, we have this as a starting material, right? This is our starting material and it is in acidic condition. So in acidic condition, we have to protonate first. So we will protonate carbonyl carbon. Sorry, this oxygen. Okay. So that's why I have written here OH. Protonation is taking place here. Then this group will 4,7 carbon will migrated over here, and this will go like this way, and it will open up this way. Now after getting this one, this intermediate, now it will undergo a aromatization, because positive charge is generated over here. We have here H hydrogen H and here aromatization will take place, because aromatic compounds are more stable compared to the non-aromatic compound. So that's why this one will form bond this way, and we will get this as a product. So all of you know here what is the product. So this is the case for 5-member ring attached here. Here we have 4-member ring attached. So what we will get here as a product? All of you know that phenyl ring will be there, right? Phenyl ring will be there. Now here we will have 5-member ring, right? What is the correct answer? Option number A. Okay. Why second one is not correct? Because aromatization is missing here, so that's why it is not stable that much. And here also one double bond is coming over here, which is not correct according to the rearrangement reaction, and this is also incorrect option. Okay. Now let's move to the question number 6. Here the correct statement about the following reaction is: the product is, the first option is written here, given here, the product is 2-chloropyridine-3-amine and the reaction involves nitrogen intermediate. The product fluoro 3-amine and reaction involves radical intermediate. And the product 2-hydroxy intermediate nicotinamide and the reaction involves benzene-like intermediate. The product, and the fourth option is product is a 2-hydroxy nicotinamide and the reaction involves the addition elimination reaction mechanism. So first of all we will write the mechanism for this question, and then we will choose the correct option. So I have given here the mechanism. In step 1 what will happen? All of you can see that our question is this way only. Here we have amide group, right? Amide, and here one halogen group is there. So the same way we are going to discuss. Yeah, here we have amide group here, right? And in first step this OH minus will take up this proton, and it will become a double, it will form a enolate enamine type of intermediate. We can say enamine, right? Enamine. So here you can see that it will abstract the proton. In first step deprotonation of the amide will takes place, and amide of the type are about, these type are acidic as water. So here conjugate base are present at equilibrium in aqueous base. So that's why the enolate ion will generate. Okay, here enolate ion will be generated. Now in second step reaction of the conjugate base of amide with bromine will takes place, and the product of this step is N-bromoamide. Here you can see the arrow pushing. Yeah, this way, and here it is a way of arrow pushing for this mechanism, and we will get the N-bromoamide. After getting the N-bromoamide, in next step again the proton will be abstracted by OH ion. Sorry, this one. So deprotonation of N-bromoamide will takes place. Amide will takes place, and the electron withdrawing effect of the bromine substituent reinforces that the carbonyl group and makes the N-bromoamide even more acidic than the starting amide. So this is the N-bromoamide we are getting, and this is more acidic compared to this one because of this deprotonation. Okay, after getting this amide, N-bromoamide, The next step is a rearrangement of conjugate base of the N-bromoamide. So here the group R, this group R migrate from one carbon to nitrogen, and the bromide will behave as a good good leaving group. Okay, so it will form here bond, and this bromine will knock out, and the product of this rearrangement will give the N-isocyanide. This N-isocyanide. After getting the N-isocyanide, in next step, the hydrolysis of isocyanide will take place by base catalyzed addition of water to form an alkyl carbamic acid. You can see here. Yeah. OH. So here hydrolysis will take place to give the an alkyl carbamic acid. Then in last step, with step number 6, the N-alkyl carbamic acid is unstable and it dissociates to an amine and carbon dioxide. It will, the lone pair will push electron here, and this will go here. This electron movement will go like this way, and we will get here carbon dioxide plus amine. This carbon dioxide will get converted to carbonate ion. Okay, and we will get here primary amine as a product. Okay, primary amine as a product. So here in this reaction we have to find out the correct option. So the product, as all of you know, that the reaction is going through nitrine intermediate, right? So that's why the correct option is the product 2-fluoropyridine 3-amine, and the reaction is amine is our, sorry, I will write here product. Fluoro group will remain as it is. Here we will have amine. Now the product is 2-fluoropyridine 3-amine, which is this one, right? So the correct option is this one, where we have this 2-fluoropyridine 3-amine, right? So we got this one, and in second option also we are getting this answer only. But the difference is here, this is not the radical mechanism we have written. We have shown here, this is a nitrine intermediate. The reaction is followed by nitrine intermediate. So the correct option is option number A. Okay. Now the question number 7 is here. Osmium tetroxide mediated dihydroxylation of the following compound led to the formation of following diols as exclusive product. So we have discussed this osmium tetroxide mechanism earlier, and here we can see that we have this bridging nor-boron type of structure, and here we have, you can see that here we have two hydrogens, right? Two hydrogens, and here we have hydrogen, and here also. Now if the approach of this osmium tetroxide will take place from below the plane, or it can happen from above the plane, there are two possibilities. If it will takes from below the plane, it will it will face the hindrance with these two hydrogens, because these are close to these double bond. Just imagine in 3D, this is a cap like structure which is above the plane, and this is the downside. If osmium tetroxide is approaching this double bond from downside, it will be observe the hindrance with these two hydrogens. When it will be attacked from the first front side, these two hydrogens are there, which is flag pole, and it is not hindering that much. So that's why, because of this one, this upside attack is favored because of hindrance, less hindrance. Okay. Now this is for this type of product, this type of reactant. In this case, reaction B, here you can see two methyl groups are there. So two methyl group have H, 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 right? Here also it is this way, H, and here we have H, here H. Now, if osmium tetroxide will attack from front side, it will be face hindrance from by these three hydrogens. But if we will approach, if it will approach from downside, it will hindered by these two hydrogen only. So the top side is more hindered compared to the downside. So that's why the attack will be favored from downside because of the hindrance again, and that's why we will get this as a product. So according to the question, there are four options given here. So the option number one is as shown above. In reaction A, the approach from top face is preferred, which is the correct thing. Approach from the top face will prefer top face. And here the second option is given as shown above. In reaction B, the approach from bottom face is favored, which is again the correct one. Bottom face attack. Hindrance here is deciding the product. Hindrance is the main factor here. Okay. So the option number 2 is also correct. And the third option is given the methyl group hinders the approach in B and reversal in facial selectivity is seen, which is also correct. I told you this methyl group is hinders the top approach of osmium tetroxide. That's why we are getting a bottom face favored attack of osmium tetroxide. So that's why all of the above option is the correct one. All of the above. Okay. Now let's move to the next question. This is the mechanism for osmium tetroxide. I have discussed earlier also, so I'm not going to give time here. Okay. Now question number 8 is given here. The question number 8 is identify the correct intermediate through which the Wittig reaction is proceed. So we have discussed earlier also. This negative charge will attack on this carbonyl center. Okay, we will get here PH O minus. Okay, then it will attack here. This way. So this is the intermediate we will get here. So in these four options you can see that this is not the correct thing. Here we are getting this type of 4-member cyclic ring which we are getting here. Okay, so this is the correct option. In option number 3, the first this 4-member cyclic ring is not oxophosphating, so oxygen is outside the ring, which is also incorrect. So the correct option is option number 2. We have discussed. Yeah, I forget to write here. Yes, I forget to write here. The phenyl ring is here. Okay. Yeah. Now. Okay. This is the product we are getting here. is a mechanism for Wittig reaction. They have discussed already. In question number 9, the major product expected when 2S3S 2,3-dimethyl cyclohexanone is treated with MCPBA is. So here this is the reaction of 10. Okay. Yeah, sure. I have 3 to 5 times. 2 hours I have. Yes, I know that. So I will finish 10 questions. You can join that class also if you want. Yes. Okay. Otherwise, a recording will be available on YouTube also. Okay. I was getting some issue with the internet, so that's why I got late. So I will try to finish earlier. So here we have question where MCPBA is used. Okay. So you can see that here we have MCPBA. So this is a type of reaction which is called as Baer-Villiger reaction. Baer-Villiger reaction. So in Baer-Villiger reaction, I will show the mechanism first, how the reaction is taking place. So here you can see that we have carbonyl carbon and these are two different R group which could be anything. Okay. So here we have per acid, meta chloro per benzoic acid. Okay. So MCPBA is here. You can see the arrow pushing here. This oxygen lone pair will take up the proton and it will form the intermediate like this one. Then it will attack another molecule of peroxide acid and followed by deprotonation. You can see here this lone pair is again pushing at attacking on this carbonyl center and this bond will get open up. After getting this intermediate, it will take up the proton from another perbenzoic acid and it will give you a product intermediate like this way along with this one. Okay. So here you can see the arrow pushing. You will get this one as an intermediate and this acid will get knocked out. After getting this one, this lone pair will again push here and it will form double bond over here and you will get the intermediate this way. Then this oxygen will push lone pair of electron and it will again get open up and we will observe this intermediate with two oxygens where we in earlier we have started with only one carbon center. Okay. Now after getting this one, this deprotonation will takes place by this perbenzoic ion perbenzoic we can say because instead of R we have here benzoic acid benzene ring. Okay. So it will get abstracted by this anion and we will get this as a regeneration of perbenzoic acid followed by our oxygen inserted product. So here you can see that the oxygen is getting inserted between this carbonyl carbon and the R2 group. So in our question we have here uh, this is the carbonyl carbon and this is alpha carbon and alpha carbon. So either oxygen can be inserted over here or it can get inserted here. So as per the uh, migrating aptitude and the stability, the always the oxygen will get inserted between the carbon which have highly substituted carbon atom, which is the highly substituted carbon atom. So here we can see that here methyl group is there and this is a tertiary carbon compared to the this one which is a secondary one. So that's why the oxygen insertion will take place between these two carbon and we will get the product which will look like this way. 7-member cyclic ring. Sorry. Yeah. Oxygen and methyl group methyl. So this is the way we are getting here the product. So the correct option is option number 2. Why option number 3 is not correct? Because here the stereochemistry is altered. Here this methyl stereochemistry will remain unaffected. Okay. So that's why the correct option is option number 2. and here oxygen insertion is taking place between these two carbon, which is also incorrect. This is also incorrect. Okay. Now let's move to the last question, question number 10. What will be X and Y in the following reaction? So here in earlier when I started the class, at that time I have discussed about the Woodward and Prevost condition, oxidation reaction condition. So here when we have this cis olefin, this is a cis, or we can also say Z olefin. Okay, Z olefin. So in this Z olefin, we have two different reagents here, reaction condition here, Woodward condition and Prevost condition. I have already told you the difference between the Woodward and Prevost. So this is a mechanism for Woodward condition reaction, Woodward. Okay. So here when the in Woodward reaction condition we have again I2. So here it is I2. It will attack on I and it will get I minus here knockout. So here we will get this epoxide type of intermediate where here is iodine. Okay. Then we have acetate ion minus OAC. Okay. Acetate ion will attack and open up this tricyclic intermediate. So we can write this way. It will open up this way. Okay. So we will get the intermediate, this neighboring group assistance. Okay. Now here this oxygen will attack on this carbon, this iodine will knock out to give the 5-member cyclic ring here. Okay. After getting this one, then hydrolysis will take place. So hydrolysis will take place, it will attack on here this carbon and it will give you an intermediate which will look like this one. Then protonation will take place, again hydrolysis will happen, and after the hydrolysis we will get OH at here. So as you can see that this mechanism is going through the 5-member cyclic ring intermediate and it is giving a product where uh, the same acetate ion is giving the another hydroxy group, right? Same head. So the attack is from same side. So when this is going through a 5-member cyclic ring, so both the O oxygen are on above side or below side. So both are on same side. So in Woodward reaction condition, we will get both the hydroxy group on same side. I told you earlier also. But because here we have tricyclic intermediate formation, it will always form at less hindered side. This tricyclic intermediate will form at less hindered side and then the acetate ion will attack from the opposite side. So that's why it will always give you a hindered side product. So the mechanism is showing the reason behind it, because the tricyclic intermediate is forming on the opposite side where the less hindrance is present. So that from the hindered side only acetate ion can attack and it will form the 5-member cyclic ring which will give you the syn product, syn diol. So this is a Woodward reaction mechanism. And talking about the Prevost reaction mechanism, in Prevost reaction mechanism again we have I2, but here what will happen? Here it will attack on iodine, again this intermediate will form, right? Again the attack will acetate attack will be from the opposite side, but here we have this acetate attack from this side and this 5-member cyclic ring will form, but here another acetate ion is there which will attack on this carbon atom. So in previous case there was no there was the same acetate ion which was giving the hydroxy group, but here the another acetate ion is attacking over here and it will become intermediate like this, it will get open up. Okay. So after getting this intermediate, because it's attacking from opposite side from the this bond, if it is on front side suppose, front side, it is attacking from back side. So that's why it will give you a anti-diol. Previous one was giving a syn-diol, it is a anti-diol. Okay, anti-diol. So this is the mechanism. So here in this case we will write down the correct answer. So here we have cis olefin, right? So according to our mechanism, here tricyclic iodine containing ring will form here. Okay, then according to the Woodward reaction condition, here I will write the common intermediate which will form here. So this is the common intermediate will form here, right? Okay, after this one I am writing here R1 R2 on behalf of these two group. So here acetate ion will attack again, and another in previous condition another acetate ion will attack and it will get knocked off. So here we will get trans product. So it will look like this one. R1 O will remain here, H OH, right? And in this case we will get the syn product. So if it is like this way R2, so we will get syn product. So now check the options. Here it is written these two groups are written trans to each other, right? If you will rotate the stereochemistry. If you will think about the stereochemistry, you will observe that both are front side. So if you will write in a plane these two groups, just rotate by 60 degree. So you will get that. Okay, I am writing in a plane. Okay, so if I am rotating it by 60 degree, and here also it is by, so I am making on plane. So this H will come on upside, right? Just imagine in 3D, this H will come front side if this will go down, and this OH will become on back side. So this OH will become on back side and H will be on front side. And with this, if talking about this carbon, if it will get rotated and in plane, so what will happen, this OH will come from front side and H will go remain will back side, right? Just imagine in 3D if you know the stereochemistry, because this in this class I can't explain all the stereochemistry things, so that's why I'm writing directly OH front side. So this is the pre-worst. So here you can say that, see that both the diol are anti to each other, right? Anti. So that's why here we can see that in X condition we are getting anti only, and in Y condition we will check here. Again we will rotate the first carbon and we will get the same stereochemistry, right? Because this is the same. And talking about the another carbon, here again we have same state. So both the structures are same. No need to convert. So this is not the correct answer, because both the structure will not be same. We know in the product between product with the Woodward condition and Prevost condition. Hmm? Yeah, second will be the correct one. So always write down the what? Yes, Woodward will give the cis diol, syn diol, and Prevost will give the trans diol. So the correct option is option number, yes, yes, second option. So you can convert it by rotating by the both the carbon by 60 degree, or anything you have to imagine in 3D. Then only you will get the correct answer. So you check all the 4 options and which is the correct answer, you analyze by yourself. So this is the correct answer we are getting here. So these are the questions for today's class. I hope all of you understood. Those who are going for other classes, you can go to that class. I will just give the summary and I will upload this today's class recording on YouTube. You can go and watch that also later. If you realize you have missed something, you can go and check the YouTube class. Okay, thank you so much for your attention. Yeah, sure. Okay, so the summary for today's class I'm going to give is, we have discussed here 10 questions. The question number 1 is about the rearrangement reaction, where we have to identify the major rearrangement product of the following reaction. So here we have here this starting material. We discuss here that the protonation will takes place because this is in acidic condition. Here protonation will takes place and we will get this as a starting material. Okay. So here we have carbocation formation will takes place at this center, and then after carbocation formation, the migration of this group will takes place because this 5-member ring is more stable compared to the 4-member. So that's why carbocation will be generated over here at this center, and then chlorine Cl- will attack to give the this as a product. So the correct option is option number 1. Then we have discussed later about the major product formed in the following rearrangement reaction. So we have discussed the Wittig reaction, where we have seen that so here we have seen that this CH2 minus is attacking on this carbonyl center and it's formed the intermediate like this one, and then later this O minus will attack on phosphatine, phosphorus atom, to form this 4-member cyclic ring phosphatine, and after this one rearrangement will take place and elimination of triphenyl phosphine oxide will take place, followed by the product formation, which is this one. So this is the product we are getting by Wittig reaction. Then we have done the reaction with osmium tetroxide and we have discussed the mechanism here. And in this case, we are getting a diol. We have discussed already the mechanism, which is shown here. So after getting the diol, it will undergo a, after getting this diol, it will undergo elimination, and here chlorine ion will attack. So we will get this as an intermediate. After getting this intermediate, the primary carbocation generation will take place, followed by migration of the neighboring group to form the 7-member cyclic ring, and then this 7-member cyclic ring will give you the ketone by pushing lone pair of oxygen electron here, and the correct option according to this mechanism is option number 3. Then we have discussed the question number 3, where we have to find out the uh, correct combination of the product. So here we have discussed that in first case the mechanism will be like, because we have used the excess of butyl lithium, deprotonation will take place. Deprotonation will take place here, and we will get the intermediate this way. this way. Okay. Then after this one, because excess of butyl lithium is used, again the deprotonation will take from this alpha carbon, either from this side or this side. So I will write from this side, and we will get here negative charge will be generated over here and will remain like this. So this negative charge will push here and it will go like this way. So here we will get the intermediate. Okay. Now this will form bond here, and N3 minus N3 minus TS will knock out to form the intermediate, this one, which is also this one. You can write this way also. Okay. So now the electrophile will approach here. Sorry, it will attack on electrophile to give the product. So here, according to this intermediate, this is our P. So this is the correct one and this is the correct one. So either the second option is correct or the fourth option is correct. Then we have discussed that it will attack on carbonyl carbon, benzaldehyde. Okay, so this is the correct option, option number 2. We have discussed earlier. I have shown the mechanism also. This way you can check this one if you got any doubt. Then we have discussed the question number 4, where we have discussed the major product. This is an example of pinacol-pinaclone rearrangement. In pinacol-pinaclone rearrangement, because it is in acidic condition, protonation will take place at any of the hydroxy group. Because here two phenyl groups are present, this here protonation carbocation will be more stable. So that's why the protonation will happen at this hydroxy group, and it will become H2O, and after the elimination of H2O minus H2O, we will get the carbocation generated over here. Then migration will takes place to form the 6-member cyclic ring. Then after this one, this oxygen will push electron here, and it will give you a this 6-member cyclic ring as a product. So our product is this one. So according to the question, the correct answer is option number 2. Okay, so here we have the same question, similar question here. So in this question we have discussed that here we have 4 members ring, here we have 5-member ring. So the protonation will take place first of all at this carbonyl oxygen, and then after protonation this bond will migrate over here, followed by this arrow pushing will takes place to give the this bicyclic ring. After this aromatization will takes place to give the product. So here, because here we have 4-member ring, it will become 5-member ring, and the correct answer is option number 1. Then we have discussed the question number 6, where we have to find out the correct statement. Here we have discussed the mechanism for this type of rearrangement reaction. We have discussed that here amine will form, right? So amine, according to the question options, amine is only in option number 1 and option number 2. So 2-fluoropyridine is we are getting here, and the reaction is proceeding via nitrogen intermediate. So that's why the correct answer is the option number A. Here we have discussed the mechanism. All the steps are discussed in detail. You can watch the recording if you want. Yeah, then we have discussed the question number 7, where we have discussed about the osmium tetroxide approach. Either it will approach by the top phase or it will approach by the down phase. So we have discussed that in first case, because here both the protons are there, hindrance is not there. And compared to the bottom phase, it will prefer always the top phase because of less hindrance. So that's why this is the product. But in the second case, here we have two different methyl groups, and these two methyl groups are showing the hindrance for the top phase. That's why bottom phase will be more favorable. So that's why the option A is also correct, because option A is in reaction A the approach from top phase is preferred, which is the correct thing. And in option B it is written that the approach from the bottom in reaction B the approach from the bottom phase is preferred, which is also correct. Option 3 saying the methyl group hinders the approach in B, and reversal in facial selectivity is seen, which is also correct. Because of methyl only the reversal uh, selectivity is taking place. That's why the correct option is option number 4, all of the above. Then we have discussed the question number 8, where we have discussed about the Wittig reaction. Wittig reaction mechanism, all of you know that, so I have written directly here. So earlier I have discussed here. So 4-member cyclic ring will form here. 4-member cyclic orthophosphatine ring. So according to the option number B is correct. Okay. Then we have discussed the question number 9, where we have discussed the Baeyer-Villiger reaction. Baeyer-Villiger oxidation. Okay. So in this oxidation we have discussed the oxygen insertion either from between these two carbon or between these two carbon, because I have told you the more stable one will be the more hindered carbon. So that's why the insertion of oxygen will take place over here, and the correct option according to this one is second one. The mechanism I have discussed here in detail. You can see and check this mechanism by yourself also. Let's move to the question number 10. Here we have two different type of oxidation. One is Woodward condition and the other one is Prevost condition. So I have discussed the mechanism for both the condition. In Woodward condition, all of you know that here tricyclic ring formation will take place, iodine included, and then acetate ion attack will take place, followed by ring opening, and then again this oxygen will attack over this carbon to knock out the iodine ion minus, and it will form this 5-member cyclic ring. After getting this 5-member cyclic ring, hydrolysis will take place, and then again followed by protonation, then further hydrolysis will take place to give the syn diode. In previous case we have discussed that till here the mechanism is same, but after this one 5-member cyclic ring will form, but instead of the hydrolysis another acetate ion will attack on the other carbon, and it will give you the anti product, and after hydrolysis it will give the antidiol. So we have cleared till here that in this case in previous station condition we are getting the antidiol, and Woodward condition we are getting the syndiol. So we have to write these question options in our product form, right? So we have to maintain make the rotation of each carbon to get the both the bulky group on same plane side, right, according to our question. So if you will see the imagine in 3D, we will observe that option number 2 is correct, where in this case we are getting the X case anti diode. This is the anti diode, and this is the syn diode, which is the correct option according to our question. Okay, I hope all of you are clear till here. If you have any question, any doubt regarding this question, you can ask me. Otherwise you can go and watch the recording which is available on YouTube. I will share the link and These slides will also be available for you on Drive. Okay. Thank you so much for your attention. Thank you.